So we know a lot now about a basis for a vector space and about coordinates in a particular basis. And we also know that a vector space can have more than one basis. So we are looking at 4.7 and changing from one basis to another basis. As usual, you're going to find that the computations here aren't super taxing. The concept of why the computations work is really why we're here. And that's what we're going to spend a little more time on, is plumbing those depths. But let's start off with a couple different bases called B and C because I lack creativity. And let's refer to the individual basis vectors as B1 and B2 and C1 and C2. Okay, so let's talk about some coordinates in B. Let's just say in B we're doing, so we'll have an x vector written in B coordinates, which is going to be 4, 2. And we know there's a couple ways we can think about this. We can think about these coordinates numerically, and we can think about them graphically. So numerically, what this means is just 4 of the first basis vector plus 2 of the second basis vector. And that comes out to, let's see, that's 28, 12. You can write it that way, or if you prefer, if you like matrix multiplication better, you can write the same thing this way. That means exactly the same thing and gives the same result. So that's the numerical way to think about these coordinates in this basis. There's also a graphical way to think about it, which is to say I've got a vector that goes over 5 and up 3. See, I better make my scale kind of small. Got a vector that goes over 5 and up 3, so maybe it looks about like that. And I've also got a vector that goes straight to the right, just goes 4 units to the right. So there's 4, 0. So I've got those two. And again, my coordinates say take 4 of the first one. So 4 of these green, 4, there's 2, 3, 4. And then from there also stack on 2 of the yellow one. That ends you up about right there in R2, which we happen to know if we use standard coordinates would be 28 units to the right and 12 units up would be another way to get there. Okay, fine, that's all well and good, and really the question now is going to become how do we get there using C coordinates, C basis? What are the coordinates in C? So now the question really becomes what would be the coordinates of that same location using the basis C. So C is a couple vectors. Let's see, I'm running out of colors here. I haven't used red yet. C is a couple vectors, 3, 1, so 3 over 1 up. Probably sits about right in there. And 2, 2, what else haven't I used? Used everything. I'm reusing purple. And then one that goes kind of a straight diagonal. And there must be some way to stack up some reds and then maybe some purples and get to that same location. I don't know what that is yet. Question mark for the moment. But really, this isn't too hard of a challenge, at least numerically. I can just say I need some amount of 3, 1, and some amount of 2, 2. That would get me to 28, 12. And you can write this as, again, as a matrix equation if you prefer. And we've got, I guess, kind of our standard two ways of solving this. You could either make an augmented 2 by 3 matrix and row reduce, or since we know about inverses, we could also solve this using the inverse. Either one of those ways, I know you're good at both those, so I'm not going to belabor the point here. It does turn out when you do that, that you get 5, 2. And if we want to double check that, we can just say 5 of the first one plus 2 of the second one should still get us to this point, to 28, 12. So let's see, 15, 4 is 19, something's not right there. Oh, sorry, this was not 5. That's what I get for trying to memorize. This works out to 8. Now let's check this. 24 and 4 is 28 on the top. And 8 and 4 is 12 on the bottom. Okay, fair enough. So we found the coordinates, or we had the coordinates in B, and now we have figured out the coordinates, the corresponding coordinates in C, which ended up being 8, 2. And this process that we did works fine. We sort of had to take this intermediate step of figuring out what these coordinates corresponded to in standard coordinates, in just how many units right and how many units up, this 28, 12. Ideally, we would like to be able to transition straight from one coordinate set to another coordinate set without having to stop in between, without having to take this little journey and then back over here. And there is a way to do that. So let's take a little bit of a look at the math of what's going on here inside the matrices. So let me use some notation. Let's call this the basis vectors matrix, and this is some coordinates in the B basis. We know that ended up producing 28, 12 when you multiply it out. And we know we wanted that to be the same as using these, using 3, 2, 1, 2, so using the C matrix, we wanted to have the same results. That was that A, B, right? That's what we were trying to solve for over here. That ended up being 8, 2 when I figured it out, right? So let me just point out here that we have enough matrix algebra that we can solve this equation right here. What we're knowing, or what we started with, was the xb coordinates. We wanted to find the xc coordinates. So this is what we're trying to solve for. We can just multiply both sides by C inverse. This is one way to go about it. So let's see. Let me just stick that, squeeze that in here. We'd have C inverse, C inverse. So one way to solve for coordinates in C is to work out what C inverse times B would become. So we can multiply these together, and we can get one matrix that transforms B coordinates into C coordinates. And that's really what we want, is just some way to jump straight from B to C without having to make this stop here in the middle. So let's take a look at how that would look. We want to do C inverse times B in that order. It's matrix multiplication, order matters. So let's find the inverse of C first of all. So C is the 3, 1, and 2, 2. So the inverse of 3, 1, 2, 2 is this little fractional guy here. So that's C inverse, and then we do want to multiply C inverse times B, and B was our 5, 3, 4, 0, so multiplying those two together gives us this little guy, 1, 1, 2, negative 1. So this comes down to 1, 1, 2, negative 1, and apparently we have a matrix here that will let us jump straight from B coordinates to C coordinates. We have a change of basis matrix. That should be the magic that allows us to go this direction at least. Let's just check it out and make sure it actually works. It should be that this transformation, change of basis matrix, times some B coordinates should give us C coordinates, should give us 8, 2 in this example. So let's multiply this out, make sure we really get 8, 2. So 4 times 1 is 4, 2 times 2 is 8. 4 times 1 is 4, minus 2 is 2. Yeah. So the coordinates in B multiplied by our change of basis matrix give us coordinates in C. That's what we wanted. Coordinates in B times our change of basis matrix gives us coordinates in C. Okay, this is one way to find your change of basis, and it works very well anytime you have your full B basis and your full C basis. If you want to go the other direction, by the way, you would just do this the other way around. Or if you already have the change of basis in one direction, the inverse of it would take you the other direction. So maybe let's just recap that, and then we'll finish this video and look at another way to do the same thing when you have different information. Okay, so keep in mind our basic relationship here is if we have some basis vectors for B and coordinates in B, we want to get the same results as we would get using our basis vectors called C and C coordinates. And if you are trying to go from one coordinate system to the other coordinate system, you just figure out which one you're trying to solve for. So if you're trying to find C coordinates, solve this equation for for the C coordinates, which would involve multiplying both sides by C inverse. So you get your formula for C coordinates will be C inverse times B. And you'd crunch that together. Turn that into a single matrix, but that would be the matrix that would turn B coordinates into C coordinates. And of course, if you want to go the other way around, if you have C coordinates and you want to find B coordinates, then just solve this equation the other way. Multiply both sides on the left by B inverse, and then you'll get an equation that says B coordinates can be obtained by B inverse times C. Now that would be, again, you crunch this into one matrix. That would be the matrix that would turn C coordinates into B coordinates. And of course, if you have one of these matrices already, if you've already gotten this one, you can get the other one either just by starting over, or you can say this one and that one are inverses of each other. So you could just take the inverse of this guy to get that guy. Okay, that's one way to get your change of basis matrix, and that will work well if you want to use it on problems 7 through 10. Problems 1 through 6 are a little more conceptual, and they don't give you all of the information, so we'll have to take a different approach on those, which we'll look at in the next video.